So for the mechanical portion of our design, we used a aluminum base and frame to keep the structure together. And before we built this, we modeled the design in 3D Fusion. And then that was able to give us all of the proper measurements for where we needed to drill holes and to what width we needed to make this frame. And we designed all of this in the ECE machine shop.
Yes.
The first PCB design that we have is our power board, shown here. And the purpose of the power board is to take 12 volts input from the wall and split it into a 5 volt and 3.3 volt power planes using switching and linear regulators. And if you plug it in, you can see that it's working because both the lights for 3.3 volt and 5 volts should turn on. And this allows us to power our entire project.
The interface board uses an MSP432 with timer interrupts to generate a PWM signal controlled off of an FTDI chip used by the GUI that we will discuss later in the program. So here we have our radio board. Essentially, it's the same design as our interface board, but the two main differences are its form factor as a circle, as well as a Hall effect sensor here on the side to tell us when we're at our 0 position.
So the MSP432 on the radio board is designed to take in Bluetooth data from our computer program, which is sent to our Bluetooth module here, which is just a simple Bluetooth to UART chip. And this Bluetooth data is then structured to an LED API that I designed to send data out to our fins in a SPI-like fashion.
Here we have our LED boards, otherwise known as our fins, which have 2 LVDSs to generate a stronger signal throughout each one of the boards, and 16 LEDs in series. Each fin board has 2 JST connectors to daisy chain the signal, clock, power, and ground signals.
Boop. All right, ready?
Yeah.
Okay, so the display connects to the computer, and that's where it gets its image information as well as speed information. So we're gonna start the GUI, and it'll be disconnected at first, and then it should connect almost now, okay? And then you can take any image and you just drag it in. So I'm going to take Bucky. We're gonna drag Bucky into the live view, and it'll run a bunch of calculations and remap the image onto a donut shape, which maps to this. And then so you can see right here all of the packets that are sent and get acknowledged. So this is the radio board command line, and this is the main board command line, and then we've got a slider here to control the speed. And then so I'm gonna spin it up. And you can see Bucky, it looks a lot better in person because of the frame rate of the camera, but that's how that works. So I can slow it down, and that's it. So we were originally planning on having 12 fins, and then that kind of shrunk to 6 fins, and now it's 2 fins. And then it was originally 1 fin, but we just have 2 on here to balance it. The problem was that we didn't really, while we had all of the fins kind of communicating and we could light them all up, we just couldn't shift data out fast enough. And that might just be a software optimization that we need to make, but we just didn't have time to do that. And yeah, so it would have ideally been like a volumetric 3-dimensional display, but it works pretty well as a 2-dimensional display.
And one more thing that we originally intended to do was have our interface board send Bluetooth data to a radio board directly. We were originally using RN52 Bluetooth modules, which we were not able to figure out how to use correctly. So as a solution to this, we replaced the RN52 on the radio board with a simple Bluetooth to UART chip. So we're now able to send data from our computer program to the radio board instead of from the interface board to the radio board.